All right, good morning, guys. We're going to go ahead and start up on our review today. So getting started, given AFCE is a parallelogram and angle DAF is congruent to angle ECB. So these two angles are congruent. What we'd like to prove is that the big figure ABCD is a parallelogram. So we already know the smaller one is a parallelogram. So to get started, we write out our given information. So AFCE is a parallelogram and angle DAF is congruent to angle BCE. Now, from here, we're going to go ahead and focus back in on the properties of a parallelogram. And we know within a parallelogram that opposite sides will be congruent. So therefore, we can say that AE is congruent to FC and AF is congruent to EC, because opposite sides of a parallelogram are congruent to each other. Now, expanding upon our properties of parallelograms, I'm going to go ahead and say that angle AFC is congruent to angle AEC. And the reason I can say that angle AFC is congruent to angle AEC is because these are opposite angles. And we know that opposite angles in a parallelogram are also congruent. Now, at this point, we have straight angles up top. Angle AEB is a straight angle because it's a straight line, and same with angle DFC. So we have two straight angles here. We also have congruent angles within those. So therefore, we should be able to say that angle BEC is congruent to angle AFD. And the reason that we can say that those angles are congruent is because they are supplements of our two green congruent angles. And we know supplements of congruent angles are congruent. From here, we can prove that the two triangles are congruent to each other. So triangle AFD is congruent to triangle CEB by angle, side, angle. So therefore, those two triangles are congruent by angle, side, angle. And then from there, we can go ahead and focus on finding some properties that will allow us to prove that this is a parallelogram. So since these are congruent, these two triangles, I can say that these corresponding parts will be congruent as well. So I can say that AD, written first and third, is congruent to CB, written first and third. I can also say that FD, written second and third, is congruent to EB, written second and third. And the reason that we can say that is because those are corresponding parts when they're written second and third and second and third. Those are corresponding parts. And they're corresponding parts of congruent triangles. And we know corresponding parts of congruent triangles are congruent. So again, we can say DA is congruent to CB and that DF is congruent to BE. The reason that we can say that is CPCTC. Corresponding parts of congruent triangles are congruent. Next, well, what if I add this blue segment AE and this yellow segment EB? Well, that would create the whole segment AB. The same could be said down here with DF and FC, giving us DC. So we can say that AB is congruent to DC, and all we did is we combined these two segments together. So that would be by the addition property. Lastly, if we now look at this, we have DA is congruent to CB, and we also have AB is congruent to DC. So therefore, we can say now that ABCD is a parallelogram because we have both opposite sides being congruent, and that is enough to imply that the figure is a parallelogram. All right, here's our next proof. Given ABCD is a parallelogram, AE is congruent to CF, so these two segments in here, and we're also given that DE bisects angle ADC. So this whole angle is being bisected. So again, we start off with our givens. And then from here, I'm going to go ahead and focus in on statement number 3. DE bisects angle ADC. So if DE is bisecting the angle, it means it's cutting in half. So therefore, we can say angle 1 is congruent to angle 2, because if an angle is bisected, it is split into two congruent angles. That's the definition of an angle bisector. At this point, I'm going to go ahead and use some properties of parallelograms. So ABCD is a parallelogram. That's the whole figure here. If that's the case, I can say that AB is congruent to DC. The reason I can say AB is congruent to DC is because a parallelogram has opposite sides that are congruent. Now, as for these two triangles here, so I have triangle DCE and I have triangle BAF. So I'm going to go ahead and focus in on proving that these two triangles are congruent to each other. The way that I'm going to do that is this middle segment here, EF. So I'm going to go ahead and add this middle segment to both segments AE and segment CF. What that will give me is segment AF being congruent to segment CE, the entire thing there. And the reason that we can do that is because we're adding the same segment to two congruent segments. So therefore the result, the sum, will be congruent still. So congruent segments added to the same segment will be congruent. Next, I'm going to go ahead and focus in on the angles because I already have two sides of this triangle, so I either need this angle and this angle, or I need these inside angles. And I'm actually going to focus in on these two angles on the inside, angle CAB and angle ACD. The reason I'm going to focus in on these two angles is because we have a transversal line here. And since this is a parallelogram, we already know that AB and DC are parallel. So therefore, these two angles are alternate interior angles. We know alternate interior angles are congruent. So therefore, we know that these two angles, DCA is congruent to BAC because alternate interior angles are congruent. We now have enough information to say that triangle ABF is congruent to triangle CDE by side, angle, side. Now that the two triangles are congruent, I'm going to go ahead and work a little bit more on the angles, because again, we're trying to prove that these angles are congruent to each other, 2 and 3. So to do that, the next thing I'm going to do is I'm going to say that the full angle over here, angle ADC, is congruent to the full angle on bottom here, angle ABC. And the reason I can say that these two angles are congruent goes back to the definition, or all of the properties rather, of a parallelogram. And the properties that we're looking for here are that opposite angles in a parallelogram are congruent. Well, now we can go ahead and focus in on the triangles that we just proved are congruent, because part of the triangles are within that full angle. So I'm going to go ahead and say that angle CDE, or I can just say angle 2, that'd probably be easier. So angle 2 is congruent to angle ABF. The reason that we can say that these two angles are congruent is because these are corresponding angles within congruent triangles. So since the triangles are congruent and these are corresponding angles within the triangles, we can say that the corresponding parts of congruent triangles are congruent. Now, at this point, if we look at angle 1, we can go ahead and say that it is congruent to angle 3. And the reason I'm doing this, the reason I can say this, I have this full blue angle here, the whole thing. I'm subtracting this gray angle from it. What would I be left with? Angle 3. Same thing over here, I have this full blue angle. I subtract the gray angle from it. What am I left with? Angle 1. So angle 1 is congruent to angle 3, and the reason that you can say that is either through the subtraction property or that differences of congruent angles are congruent. Lastly, I see angle 1 is congruent to angle 2, and I also see that angle 1 is congruent to angle 3. So if I skip past angle 1, I can go straight to angle 2 is congruent to angle 3. And the reason that we can say this, well, any property that allows me to skip one is just the transitive property. So therefore, angle 2 is congruent to angle 3 by the transitive property. And with that, this proof is complete. All right, next up. FHJK is a rhombus, and the measure of angle FKJ is 120 degrees. Km is equal to 6, and we'd like to find the perimeter of the rhombus. So to get started, we're going to draw up on our figure all the given information. Now, within a rhombus, we know that the diagonals are perpendicular, so this would be 90 degrees, and also that the diagonals bisect the angles. So both of these angles will be cut perfectly in two. So if the full thing is 120, each angle will be 60 units. And again, since this is a 90-degree angle, this will become a 30, 60, 90 right triangle. Well, if that's the case, we can go ahead and draw our special right triangle. And I went ahead and I took out this triangle here that we have, and I brought it right over here. So from here, we see that we have 2x and y. Whoops, sorry about that. Let me go ahead and go back. Need to draw it all up once again. Geez, maybe. There we go. So drawing it up, here we go. So at this point, we see that 2x is equal to y, and we also see that x is equal to 6. So if x is equal to 6, I can go ahead and plug that in for x, and we have 2 times 6 is equal to y, so therefore y is equal to 12. If y is equal to 12, that means each of these sides is 12 in length, so therefore our perimeter is equal to 12 times 4 sides, which will give us 48 units. So our perimeter is equal to 48. All right, next up. Each of the following quadrilaterals always has congruent diagonals except blank. So out of these four figures, 3 of them will always have congruent diagonals. It's one of their properties. The only one that doesn't is letter B, a kite. The other ones will all have their whole diagonals being congruent to each other. So the entire thing is congruent to the entire thing. Next up, in parallelogram ABCD, angle A is equal to 2x plus 6, angle B is equal to x plus 24. We would like to find the measure of angle C. So to get started, we can go ahead and draw in everything that we know, and also the properties that we can use. And since we're using angles within a parallelogram, I'll go ahead and write out our two properties of angles. That opposite angles are congruent and consecutive angles are supplementary. So therefore, if consecutive angles are supplementary, I can say angle A plus angle B is equal to 180 degrees. So 2x plus 6 plus x plus 24 equals 180. Combining like terms, we get 3x plus 30 equals 180, which will give us 3x equals 150. Dividing both sides by 3 gives us x equals 50. Now, since we know angle A is congruent to angle C, they're going to be the same measure. So if I plug in 50 for x, for angle A, I will also have angle C. Well, 2 times 50 is 100. 100 plus 6 is 106 degrees. So angle C is 106 degrees. All right, next up, name 5 properties of a parallelogram. So we only have 5 of these. The first one is the definition of a parallelogram. Opposite sides are parallel. After that, we also know that opposite angles are congruent, as well as opposite sides being congruent. And then we just talked about some of these with the angles, so we know consecutive angles are supplementary. And the last one that we have is that diagonals bisect each other. Diagonals cut each other in two. So those are the 5 properties of parallelograms. Each of those is very important, so make sure that you know each of them for your test. All right, next up. Determine if the statement is always true, sometimes true, or never true. So this first one, if one of the angles of a parallelogram is a right angle, then all of the other 3 angles must be right angles as well. Well, since it's a parallelogram, we know opposite angles will be congruent, so the opposite angle would also be 90. And consecutive angles are also congruent, so one angle right after the other would also be 90 degrees. So as a result, all angles would be 90. So this would always be true. Letter B, the diagonals of a parallelogram are congruent. Well, having the whole diagonals of parallelograms being congruent is only true for rectangles and squares. It is not true for any rhombus, and it's not true for any parallelogram, but only for only for rectangles and squares. That's the only time it will be true. So therefore, it's not all parallelograms, but some of them, which makes it sometimes true. And lastly, if a parallelogram has congruent diagonals, then it's a square. Again, we just talked about this. Diagonals are congruent within rectangles as well, so this is also sometimes true. It's true when it's a square, but it could also be true for a rectangle. All right. Trap is an isosceles trapezoid with base TR and PA, meaning those sides are going to be parallel to one another. We also know that angle TPA is equal to 70 degrees. Measure of angle RAZ is 5x minus 8. Measure of angle ZAP is 2x plus 1. PR is equal to x plus 2. We want to solve for x and then find the length of TA. So to get started, we should probably draw all of our information on here. And once we have all of our information on here, well, one of the important things that we know is that we have these lower base angles. And since they gave us 70 degrees over here, the other lower base angle should also be 70. So we can automatically plug that in. Now, as we look at this 70-degree angle, we see that we have these two angles that are making it up. So the purple and the black angle, if I add these together, we get 70 degrees, the whole thing. So let's go ahead and set up our equation for that then. 2x plus 1 plus 5x minus 8 equals 70, because again, base angles are congruent. From here, we can go ahead and solve for x. Combining like terms, we get 7x minus 7 equals 70, which will give us 7x equals 77. So x is equal to positive 11. Once we have x, well, we need to find the length of TA. Since this is an isosceles trapezoid, we know that our diagonals will be congruent to each other. So if PR is x plus 2, TA is the exact same thing. Plugging 11 in for x, we get 11 plus 2, which is 13. So therefore, if PR is 13, TA is also 13. All right, nearing the end. If PARD is a rhombus, then what kind of angle is angle POD? Well, a rhombus has diagonals that are perpendicular bisectors. So therefore, angle POD, one of the angles that's formed by the intersection of the diagonals, should be a 90-degree right angle, because again, diagonals are perpendicular to each other within a rhombus. So knowing those properties will allow you to determine what type of angle is occurring. And our final problem of the day. Given the diagram as shown, we'd like to find B, which is the midpoint of AC. Once we find B, we want to go ahead and show that BEDC is a parallelogram. And then lastly, we want to show that it is not a rectangle. So to get started, we're going to use our midpoint formula to find point B. To find the midpoint, we're going to use points A and point C. So for the midpoint, we add our x values together and divide by 2. 2 plus 22 is 24, divided by 2 is 12. 14 plus 6 is 20, divided by 2 is 10. So our midpoint is 12, 10. Now that we have our midpoint, we're going to find the slope of each side. Now again, you can use any property that you'd like to prove that to prove that this is a parallelogram. But since I'm proving that it is not a rectangle, it would be useful for me to find slopes. If I found the distance, that'd be useful to prove that it is a rhombus or not a rhombus. But for a rectangle, slopes will be more useful because I'll be able to see if consecutive slopes are opposite and reciprocal. So first off, to find the slope of BE, we'll go ahead and use our slope formula, y2 minus y1 over x2 minus x1. That'll give us 10 minus 4 over 12 minus 9, which will give us 6 over 3, which is equal to positive 2. Next, I'm going to go ahead and find the slope of the opposite side, CD. Using the same formula, this time I have 6 minus 0 over 22 minus 9, which will give me 6 over 3, which is again 2. So we have opposite sides being parallel because they have the same exact slope. Next, let's go ahead and check BC and ED to check and see if this is a parallelogram or if it's going to stay as a trapezoid, which it currently is based upon what we know. So checking BC first, we have 10 minus 6 over 12 minus 22. That'll give us 4 over negative 10, which is equal to negative 2/5. Lastly, we check ED using the same exact thing. So for ED, we have 4 minus 0 over 9 minus 19. That'll give us 4 over negative 10, which is, again, negative 2/5. As we can see, since both pairs of opposite sides are parallel, that means that this is a parallelogram. Lastly, our convincing argument that this is not a rectangle. I don't actually have to do more work for this because we found slope. If I found distance instead, we would have to do more work. But since we found slope, we can go ahead and look at this. The consecutive slopes, BE and BC, these are not opposite reciprocals. The opposite reciprocal of negative 2/5 would be 5 over 2. The opposite reciprocal of 2 would be negative 1/2. So as a result, since consecutive sides don't have opposite reciprocal slopes, they are not perpendicular, which means that we don't have right angles and that this is not a rectangle, but a parallelogram. All right, that is it for today's notes for our review. If you guys have any questions, please let me know. But thank you guys so much for watching, and